So recall that glycolysis produces 2 molecules of pyruvate and a little bit of ATP and a little bit of NADH. Recall also that the details of glycolysis, the intermediates and all of the enzymes, like that didn't particularly matter, nearly as much at least, as these 4 questions: what comes in, what goes out, how is the energy captured or transformed, and how is this step regulated. The next major step of cellular respiration is a step called pyruvate processing. And so pyruvate is produced out in the cytosol or the cytoplasm and then transported into the mitochondria, where it is processed by this enormous complex of enzymes called the pyruvate dehydrogenase complex. And as that happens, pyruvate is transformed into a molecule called acetyl-CoA. Pyruvate, recall, has 3 carbons. It's a 3-carbon molecule. Acetyl-CoA has just 2. Well, where did that extra carbon go? That extra carbon actually comes out of the pyruvate dehydrogenase complex as carbon dioxide. Additionally, this pyruvate processing step also reduces some NAD+ and gives off an NADH. So, what goes in? Pyruvate. What comes out? Carbon dioxide and acetyl-CoA, and the energy-bearing molecule NADH. How is this regulated? Well, it turns out that the pyruvate dehydrogenase complex is actually a key regulatory checkpoint in this entire big, like, central metabolism set of pathways. And interestingly enough, there are a number of molecules that turn off the pyruvate dehydrogenase, and if you stop and think about it for a moment, I bet you can already begin to predict what those molecules are. Because in the same way that glycolysis is slowed down or turned off when there are lots of energy-bearing molecules around, the pyruvate dehydrogenase complex is also slowed down, turned off by energy-bearing molecules. And those energy-bearing molecules are things like ATP and NADH, right? We've already met both of them. In addition, the pyruvate dehydrogenase complex is also turned off by its output molecule, right? So acetyl-CoA also turns off the pyruvate dehydrogenase complex. And so there's this kind of negative regulation, this negative feedback loop. It's a motif that we've seen already. What we haven't seen already is that this step is also positively regulated, which is to say there are also some molecules that will turn it on or speed it up. And if high energy molecules and the output are slowing it down, it might make some sense that low energy molecules and the input molecule speed this process up. And so a low energy version of ATP might be AMP, which is a molecule we actually haven't seen yet. ATP is adenosine triphosphate. It's got 3 phosphates. ADP is adenosine diphosphate. It's got 2 phosphates. AMP is adenosine monophosphate. It's just got 1 phosphate. This is a very low energy molecule, and it will turn this process on. NADH. The oxidized version of NADH is NAD+. That will also turn this on. These molecules exert positive control. When there are low energy species in abundance, they speed this process up. And so, we started with a 3-carbon pyruvate. We ended with a 2-carbon acetyl-CoA. However, there's still some additional chemical energy that we need to extract, and that's going to happen in the citric acid cycle, which we're going to talk about next.